Hi, good day again to everyone. Welcome back to our lecture series in the General Mathematics class. We are now in the lecture series number 5. Our focus is the vertical and horizontal asymptote and the removable discontinuity involving rational functions. Before we are going to start, may I introduce to you again the platform that I'm using in my class. My channel in the YouTube is Agipan. So just search for the name Agipan and there you have so many lessons in there and click watch the lesson you needed in your class. Let's start. Rational function. Before we're going to discuss the asymptote, we need to recall the form of the rational function. So what would be the form of the rational function? There, f of x is equated to p of x over q of x, wherein the p of x and q of x are polynomials. And remember the limitation of our denominator, where q of x should not be 0. Remember, a rational function can have more than one vertical asymptote, but it can have at most one horizontal asymptote. So consider this graph. You remember the lecture we have last time in the series number 4? We have in here the graph of the rational function. Now you will notice in here I told you that I'm going to explain to you what is meant by this line, horizontal line, or shall we say, the horizontal asymptote. Another would be the meaning or what is meant by this hole that you can see in our graph. And what is that? We have said that that is considered to be our removable discontinuity. We are going to explain why or how come we have removable discontinuity. Another would be what would be this vertical broken line, and that is called to be now our vertical asymptote. So again, for our asymptote, we have horizontal asymptote. So a broken line here. We have vertical asymptote, a vertical or this one. And of course, the hole in here, that is called to be our removable discontinuity. Consider first the vertical asymptote. It says in here, if p of x and q of x has no common factors, then the rational function has vertical asymptotes when the q of x is equal to 0. Thus, the graph has vertical asymptotes at the excluded values. What do we mean when we excluded values? These excluded values are not included in the domain of the rational function. So you will notice in here, a rational function p of x over q of x have a vertical asymptote at x is equal to a for any value of a such that q of a is equal to 0. So again, the value of a in here are not considered to be the domain of the function or the rational function. Why? Because a in here is actually the restriction of the rational function. This a in here will make the denominator of a rational function equal to 0. And thus, as what we have said, a rational function should not have a denominator of 0. Continuing the vertical asymptote. Vertical asymptote is at x, which is equal to a, where a in here represent the real zeros of the q of x. What is this q of x? It is actually the denominator of the rational function. So we have said that the denominator should not be 0, and that you will notice the value of a in here will make the denominator to be 0. And so, this a in here will not be included to be the domain of the rational function. It says in here in the problem, show that the line x, which is equal to 2, is the vertical asymptote of the graph of the rational function 4 over the quantity x minus 2 raised to the second power. Since your q of x is the quantity x minus 2 raised to the second power, now we are going to get the value of this x. So how do we get the value of this x? Meaning, we apply the factor method. So in the factor method, we have to factor the denominator, and so it will give you a factor of x minus 2 and x minus 2. And after that, equate that one into 0. And so each factor must be equated with 0. And after factoring them, equating them to 0, that's the time we're going to look for the value of the x. You will notice that we have the same values of x with regards to our two factors given. So you will notice in here, x is equal to 2 is the same as this one. Meaning, the value of your a in here is actually 2, which is the restriction of our denominator in the rational function. So, but with that, our vertical asymptote would be x is equal to 2. This shows that x is equal to 2 is the restriction of the rational function. The domain of the rational function are all real numbers except positive 2. Continuing the graph of the functions we have a while back, you will notice that after having now the restriction, which is positive 2, now we assume the value of x. So I assume in here from 1.5 to 2.5. You will notice I included the 2 in here to show to you that when I'm going to calculate this one, it will not give me a result of f of x. So meaning to say, if I'm going to make use of this 2 uh, and replace or evaluate this function I have in here, it will give me an undefined rational function. And that is the very reason we say 2 in here is the restriction of the rational function, or it is not included in the domain of the rational function. Okay, let's try to consider the graph. So you will notice that I have in here the graph of my rational function. So if the graph is coming from the left side of your positive to the restriction of the rational function, you will notice that as it come closer and closer to positive 2, it will go up, it will rise, go up, and it will not cross this vertical line, which is the value of the x, positive 2. Why? Because this vertical line in here now is considered now to be my vertical asymptote. So you will notice that as the graph come closer and closer to the vertical line, it will not cross the vertical line because this vertical line in here is considered to be the vertical asymptote of the rational function. The same true with the value of x, which I computed coming from the right side of the positive 2 going toward the positive 2, you will notice the graph. As it comes closer and closer to your positive 2, it will go up and it will never cross this vertical line. It will never cross this vertical line. Why again? This vertical line, which is created by your x, which is equal to 2, is considered the vertical asymptote. Another concept that we're going to discuss will be the horizontal asymptote. So it says in here, horizontal asymptote is determined by looking at the degrees of the p of x and q of x. But we have to consider this illustration. You will notice in my illustration, p of x is a polynomial, which is the numerator of the rational function. Q of x is the denominator and considered to be polynomial. We have to understand what is the leading coefficient of p of x and leading coefficient of the q of x. When we are talking of the leading coefficient, it speaks of the coefficient, numerical coefficient of the first term of the polynomial, be it numerator or denominator. Okay, now we have in here the f of x is equal to 3x over x raised to minus 1. And you will notice that the leading coefficient of p of x in here is 3. 3 is the leading coefficient of the first term, but we have only one term. So our term is 3x. So the the leading coefficient we are talking is the numerical coefficient of this term. So now what about the leading coefficient of the q of x? The question is, what is the first term? The first term is x raised to. Now, when we are talking of the leading coefficient, it is actually the numerical coefficient of this first term. What is the numerical coefficient of this first term? It is 1x or 1. So continuing the problem, our leading coefficient is 3 and 1. If the degree of 3x is less than the degree of x raised to 2, the horizontal asymptote is located at y is equal to 0. Again, the horizontal asymptote is located at y is equal to 0. Why? Because the degree of the 3x is less than the degree of x raised to 2, which is the q of x. Consider this one. Where is the location of the y is equal to 0? We have in here. So this one is my horizontal asymptote. Where it is located? It is located with y is equal to 0. So again, what is this line? It is considered to be the horizontal asymptote. Now, what is the effect of this horizontal asymptote when we will be plotting function or when we will be graphing function? Here is the effect. As the graph goes up and come closer and closer to my horizontal asymptote, this graph will not cross. Okay, it will not cross this horizontal asymptote, meaning it will not touch this horizontal asymptote. You will notice that when my graph will be coming from the upper part of my Cartesian plane and it will go down, it will not pass my horizontal asymptote. So you will notice this graph in my illustration. It is shown by my circle. The next rule in the horizontal asymptote is, it says in here, if the degree of p of x is equal to the degree of the q of x, the horizontal asymptote is the leading coefficient of p of x over the leading coefficient of the q of x. Now, for us to understand this rule, let's consider this problem. Find the horizontal asymptote of f of x, which is equated to 3x plus 1 over 2x minus 1. To understand the rule, we have to dissect one by one every part of this rational function. Now it says in here, the degree of the numerator is equal to 1. Where is this one came from? It is actually came from the exponent of 3x. Okay, so what is the exponent of 3x in here? It is 1. What about the degree of the denominator? It is also 1. Where did this 1 came from? It is actually the exponent of the 2x, which is 1. So meaning to say, in here, the exponent is 1, the exponent is 1. So they are equal. With that, what would be its horizontal asymptote? Of course, the horizontal asymptote of the problem, if the degree of the p of x is equal to the degree of the q of x, which is 1 is equal to 1, the asymptote would be y is equal to 3 over 2. Now here is the leading coefficient, 3 over 2. That is the meaning of this term. Leading coefficient of p of x, leading coefficient of the q of x. So what is the leading coefficient of p of x? 3, which is 3. The leading coefficient of the q of x, 2, which is 2. And that will define the horizontal asymptote of the rational function. Let's consider its graph. Now, since we have the horizontal asymptote, now we have in here now the graph. So as you can see, I have in here the horizontal asymptote, which is located in 3 over 2, or that is the same as between 1 and 2. Y is equal to 1 and 1 half. Okay? 1 and 1 half. So that would be my horizontal asymptote. Next, letter C, rule in the horizontal asymptote. It says in here, if the degree of the px is greater than the degree of the q of x, if the degree of p of x is greater than the degree of the q of x, then there is no horizontal asymptote. You cannot have horizontal asymptote of the rational function if the degree of p of x is greater than the degree of the q of x. So consider this one. Our rational function is f of x is equal to 3x raised to 2 plus 1 over 2x minus 1. Let's try to see the degree of the problem. Okay, so the degree of the numerator is 2. Okay, and the degree of the denominator is 1. Again, the degree of the numerator, this one exponent, is 2, and the degree of the denominator is 1. So 2x raised to 1 in here. Okay, so you will notice, as the rule says, since the degree of the numerator is greater than the degree of the denominator, what is the degree of the numerator? 2. What is the degree of the denominator? 1. Then there is no horizontal asymptote. To continue discussing the rational function, consider the removable discontinuity. For us to have understanding of the removable discontinuity, now let's take a look this problem. F of x is equated to x plus 2 over x raised to 2 minus 4. Okay? Now, you will notice that I have in here the problem, and I took the factor of the denominator. Now, the use of this denominator is for us, the reason why I factor the denominator is for us to compute immediately the restriction of the rational function. So the restriction would be, we have in here positive and negative 2. But the vertical asymptote would be positive 2. What would be the domain of the problem? The domain of the problem are all real numbers except positive 2 and negative 2 coming in here. So x plus 2 is equal to 0, it will give me my negative 2. And another one, x minus 2 equal to 0, it will give me positive 2 as the value of my x. These values of my x, positive and negative 2, are considered to be the restriction of the rational function. But the vertical asymptote is only at positive 2. Again, what are the domain of this rational function? The domain of this rational function are all real number except positive and negative 2. Why? Because positive and negative 2 are all restriction of the rational function. It will make the denominator 0. Now, the question is, would, would that not be the vertical asymptote? No. The vertical asymptote only is the positive 2. Would it not include the negative 2? No. Why? Because that negative 2 now will be the location of the removable discontinuity. If you remember, this removable discontinuity is the hole under the graph. Okay? It is the hole that you can see under the graph. Why do we have a hole under the graph? So as you can see, we have in here the hole. Okay? Why do we have the hole or the removable discontinuity of this graph? It is because it says in here, hole is the removable discontinuity. This result from the common factor of the numerator and then the denominator. As you can see, my common factor is x plus 2 over x plus 2. That is the reason why we have removable discontinuity, and this negative 2 will not be considered to be a vertical asymptote. The only vertical asymptote we have is positive 2 and this one. So here is the location of the negative 2. Supposedly, generally, it is supposed to be the location of another vertical asymptote, but because we have a common factor, this will be now our removable discontinuity. I know that as we go on with our lesson deeply studying this general mathematics, things are more complicated. Okay, so please find time to smile. Okay, please find time to smile. Okay, yeah. So again, you can always beat this general mathematics if you listen and try to understand the discussion. Before we end this lecture, I hope I shared to you ideas about asymptote in my humble capacity. Please like, click subscribe button and click the notification bell so that you will always be reminded of the new lesson posted. And again, thank you for listening and good day to everyone.